I get us started.
Thank you.
Welcome to the Path Seminar Series. My name is Scott Mora, and just quick logistics. We're in a new room relative to where we've been in the past. I think we're gonna probably be in this room for the upcoming weeks. So remember how you got here, because you may copy and paste in future weeks. Without further ado, it's my distinct pleasure to introduce Professor Gabor Orosz, who comes to us from the University of Michigan. I actually first not met you, but experienced your lecture when he interviewed as a faculty member. I was a graduate student, and I remember how engaging your presentation was, and especially you had a clip from one of the Mission Impossible films.
I have it at the end. So.
Oh, you do? Okay, good, because I love that. Okay, so you all see what I love from that very first talk. And now professor in mechanical engineering and civil engineering at the University of Michigan. Prior to that, held appointments at UC Santa Barbara, Caltech, Budapest University of Technology. And, Gabor is really an expert in nonlinear dynamics, as I see it. You're training really in mathematics and physics, and you bring that flavor to, he brings that flavor to his work and is particularly famous, many of you already know, but particularly famous for cooperative driving and also robotics from a nonlinear dynamics perspective. I personally supremely enjoy hearing Gabor talk, so thank you so much for being here with us, and I hope you all enjoy the lecture.
Thank you very much, Scott. It's really nice to be back at Berkeley. So we discussed that I was here about 12 years ago, and I checked back my slides 12 years ago. I actually gave 2 seminars. One had 55 slides, another had 57, okay? So one thing I learned maybe in the last 12 years, that's a little too much, okay? So today I will have less and probably still not gonna finish. So let me start with introducing a couple of people who this work is closely related. So Tamás Molnár was a postdoc in my group and is now a professor in Wichita State University. And Charlie was a student of mine who is currently a professor in Buffalo. And Sergey is here in the Bay Area. Actually, he works for Toyota, where he leads a research group. But you will probably see him more in Thunderhill racetrack because he's also racing there often. So if you ever go up, then you may meet him. And Anil just finished his PhD. I'm not quite sure I'm going to get to his research in this talk, but now he moved to Delft in the Netherlands, and it's working with Barclay Scutter. So when I got to Michigan, I was a transportation person, right? But as we all know, it's hard to make experiments in transportation, right? I will get to that. So we decided that we're going to build our own kind of experimental fleet. So I think when Scott was there, he might have seen some of these robots kind of luring around G.G. Brown and Dow building, right? That's where the students were playing with that. So basically, we built our own cars. And we tried to get them as close to as possible for real vehicles when we were scaling them down and so on. But certainly, we understand the difference between a robot like this and a real vehicle, let's say, which later we could play with. Look at that. Okay, so this was a true car. Okay, so kind of hacked by a company and also by us. And then we had a lot of fun with that playing in M-City. And then eventually, we even went higher, so we played with animals like that, and then you can see that the truck was actually bigger than the group at that time. So and we learned a lot, that it's actually not the same. We already know that it's not the same running something in simulation and putting in our hardware, but it's certainly a big difference as you kind of move between these different hardware types, and you learn a lot on the way what is possible and what is not. So just with the first one, I have a quick video about it, which I hope I can play.
Ooh, nice.
Have you ever been annoyed by pressing the throttle and the brake in a crazy way during a traffic jam? Actually, controllers can take place of human reaction and will have far less delay in this kind of situation.
Our project aimed at building a test bench for this kind of connected vehicle topics. We build ground robots with V2V communication.
This summer, we work on sensor calibration analysis, lab view programming, and solving hardware and software problems. Our vehicle is driven by a DC motor and steered by a servo. Sensors include a motor-embedded tachometer, a laser for car distance detection, and 2 encoders for localization purpose. All the actuators and sensors are governed by National Instruments compact reel, and vehicles can communicate with each other through tablets.
So as you can see, at that point, we already were playing with the connectivity between the vehicles, and this is how kind of a real experiment looked like. I will show you in the right by explaining what we did. But indeed, we could design every single piece of this vehicle, right? So all the boards actually were designed by Wuming, who is a student on the right, and then. Whatever we kind of did in equations, we were able to replicate it pretty well in the experiment. So in particular, we're playing with that simple controller in this video, where we are trying to match the speed of the vehicle in front of us. So that's why we have this term here, okay? And we also kind of set our velocity according to the distance, or the distance according to the velocity. And those people who work on car flowing models, this is indeed exactly the optimal velocity model, right? So this was discovered in many different ways, and this was actually implemented on this vehicle. And turned out that we could actually follow that range policy pretty well. And then, as already the student mentioned, the delays were much smaller than in the real vehicle, so we were able to replicate the dynamics pretty nice, okay? So then we got really cocky. And so when we said, well, can we do it on a real car? Okay. In this case, you see the video from the vehicle at the front, and the one is following us in the rear. And we were driving on M-City. So this map on the left is what we call M-City. This is a test track at the University of Michigan. And the colors are indicating where we're going faster and slower. And actually, we did pretty well. So the same controller could be transferred. We already used connectivity. It was actually easier to run the experiments with connectivity than with sensors, because sensors often miss the other vehicle and so on. Connectivity just knows where it is. And this is a pretty harsh braking at the front, which you don't see, because the rear is so relaxed that Sergey put out his hand on the window and we were just driving pretty nicely. Okay. So as I mentioned, this is where we started to get interested in connectivity. But if you look at this experiment, you can say, well, actually, you could do it with sensors, right? It's not necessary to add connectivity to the picture. So we started to think, well, let's show something which is non-trivial. Okay, so maybe this is the simplest non-trivial example where connectivity can get used. Okay, so I have 3 vehicles here. This connected automated vehicle is at the back, and it can sense indeed that human-driven vehicle using a range sensor. But in order to get information from that lead CHV, you need to have this connectivity. And the connectivity we use is called V2X, vehicle to everything communication. But in general, it doesn't quite matter what you're using on if it's able to generate have like reasonable latency. Okay. And really the controller which we changed is that now we are responding to another vehicle. So we simply added another term, okay, where we also try to kind of match our speed with the velocity of the other vehicle and say, well, of course, could be much more interesting controllers, and we designed many, but whenever you come down to implementation, you kind of boil it down to the simplest possible thing, okay? So in this case, we just decided to use this velocity difference, okay? And this system is already interesting because, well, you would refer to this these days as a mixed traffic system, right? We have automated vehicles, we have human-driven vehicles, which are mixed together. And one interesting thing is that what kind of performance measure we want to have? Well, obviously, we want to have safety, and today I'm not really going to talk about it so much. But you also want to have some kind of performance measure. We say this is good for the transportation system, okay? Now, this human-driven vehicle in the middle it's a human, it can do any bad things, right? So you can't control that. So what you can basically do is to try to talk about what happens at the head and what happens at the trail. Okay, so we basically created this transfer functions after we linearize the system and do the analysis, and it becomes a simple network, right? We have basically 3 connections and each are weighted with these transfer functions. And then we could create something called a head to tail transfer function. So this actually summarizes the overall effect of the black vehicle on the blue vehicle, right? There are 2 terms. So this one, the easy one, the T02, that corresponds to the direct response, right? And there is another one, which is a product. So I can actually design this T01. This is the transfer function of the CAV, but I also have this T12, which comes from the human, right? That I won't be able to design, right? So I have to kind of take it based on some model or based on some database learning or whatever I want to do that. However, if I'm able to somehow design a system, which is what we call a head to tail string stable, so this transfer function is always less than 1 for all frequencies, this unit would behave really nicely in transportation, right? Because whatever happens at the front, at the end, the tail is going to be attenuated. Okay, so this would be a jam killer at the mini scale at least. Okay, so and we did some calculations based on that. So we're playing with these parameters. So the beta 01 is how much we respond to the vehicle right in front of us, so the V1, and the beta 02 is how we respond to the vehicle, which is 2 vehicles ahead. And the alpha, we kept it something which is related to safety, okay? And it turns out that indeed, if I don't use connectivity, then it's not just that the human is doing bad, right? So this is above 1, which is amplifying the perturbations, but I won't be able to push this blue below 1, right? So there will be some parts where some frequencies, the system is going to be sensitive, and we will actually amplify these perturbations, okay? But if I crank up the connectivity gain here, then you can see that despite the fact that there is a bad human in the middle, right, modeled by this T, I'm still able to push down the blue, right? So this overall unit is going to behave very nicely. So this is very promising because we didn't have to automate all the vehicles. As a matter of fact, we only automated 1, but the overall unit we designed is actually behaving very nicely, okay? So we found it kind of very promising, and maybe we can really show that this works in real life, okay? And of course, everything is designed at the linear level, something very simple, but we wanted to see, how does it work in real life? So then we went on the track, and so it is MCD, and you will see there's a little rattling, that's just the video, and so it's hard to see the video, but one thing you can see, this guy was pitching at the end, okay? And it actually had to come to a full stop. So on the top, I'm showing you the velocity. It indeed had to stop through this chain of breakings, okay? And the acceleration reached 1g, okay? So what does that mean? If you drive that car, your entire weight is going to be on the safety batt. That hurts. My students complained a lot, okay? So in this case, the vehicle was able to avoid the crash, right? So finally it responded. It was a human driver. This was Sergey. Again, he's doing it for life in real life in the racetracks, right? So you know how to do it. But imagine if, for example, the road surface was a little wet like here, or icy like over in Michigan in many cases. You will not be able to execute this maneuver, okay? So if you say, well, if I automate this vehicle, can I do better? Okay, and the answer is yes, you will. So now you see that, especially in the acceleration, the second vehicle is still doing an almost 1g braking, but the automated vehicle is able to bring it down to half the g, okay? Half g is kind of, you feel a little bit of harsh braking, but you would be okay with that, okay? So this is what basically automation can do. And of course, we tune these control gains and tune these controllers that is kind of the best what we could do with that form. Maybe you could do a little better, but you will be always bounded by the fact that you're only responding to the vehicle right in front of you. You're not utilizing distant information. Once you turn that in, something very interesting happens. So again, the vehicle is in front doing the same kind of braking chain. But your acceleration or deceleration is about a quarter g. So if you have a cup of coffee in your hand, it would not spill. Okay, they love this experience because they would not feel the the harsh breakings and so on. So we went basically from human to automation, then we got from 1G to half G, and we went from automation to connected automation, we went from half G to quarter G, okay? And this maneuver you can do on ice and snow. This would work, okay? So you would be able to execute this. So we got really excited about it, right? And of course, we wanted more. So what we did was we went out, okay? And then we found this beautiful road in Michigan. This is farmland, okay? So typically, these cars are very unusual there. They are typically pickup trucks, okay? And that's why they called the police multiple times because they didn't know what the heck we are doing there. So this is the section we actually chose about 13.5 kilometers, about 8 miles, okay? And basically you have the way there, uninterrupted driving American dream, okay? And of course, the question was always, who drives the Dodge Challenger, right? So this day, I think this was the guy who was the lucky one. So we basically created our own little transportation system, right? And it's not exactly the same as going on a real highway and doing things. So later we did that, but not with 8 vehicles. But at least it's as close to as we come to a traffic scenario, okay? So what did we find? We were testing, again, different configurations. We started with the human, again.
By the way, can I ask
Yes.
if there were no intersections or?
So there are intersections where you have the right of way. So we just drive through.
I see, okay. So essentially uninterrupted.
Uninterrupted driving for 8 miles, which was very nice. We actually made all the vehicles connected, so we collected all the data and anyone wants to use it, I'm happy to share it. Just let me know. So it was a lot of fun, but of course, you always kind of shaking a little bit because you want to go back to campus with the same number of students you took out for the experiments, right? So this happened.
How far apart were they?
So they're supposed to do car following. So the only instructions the humans got is that don't lag behind, right? Because then our experiment would not really work. But otherwise, they were just driving normally. The speed you see reached about 25 meters per second, which is about 90 kilometers per hour, which is actually 55 miles per hour. That's the speed limit in that section of the road. So here I'm only showing the velocity and the for the brown vehicle, right? So this was actually, these perturbations are done by the driver of the brown vehicle, and also showing what the blue vehicle was doing. And you can see that it was definitely getting much worse, right? So if you look at how much the brown reduced the speed, by the time the wave reached the blue one, it actually was much, much worse. And you can see one of the zooms here when I'm showing all the vehicles. And you can see this kind of string instability in the system, right? So this is, every vehicle is keep amplifying, what's happening in front of them. So certainly we observe it a lot in traffic. And one of the negative things which comes out of it, that the energy efficiency is also getting worse and worse. So we use this energy consumption per unit mass to calculate the energy consumption, because we could compare different vehicles, right? Some of them had different mass and so on, and we didn't want to care about the engine and all those things, right? So in here, this is the velocity, this is the acceleration, and this is the drag terms, but often we could neglect it. That was actually not so important. It was much more important that we are accelerating and decelerating. And so basically, this is velocity times acceleration, right? If I multiply it with mass, that would be power. Integrating power is energy. Okay, so I drop the mass, and that's why it's got energy consumption per unit mass. And then this G function is used that we only count that we burn energy when we accelerate. When we brake, we are dissipating energy, and we say we would not consume energy. Of course, in an IC engine, that's not quite true, but it kind of works pretty well. What you see here is that as you go along the chain from brown to blue, this is getting worse and worse, right? So certainly along this 500 seconds, this is the consumption of the first vehicle, and the last vehicles in the chain, they are really, really bad, okay? We actually didn't go out there with maximizing energy. So we didn't have it, or minimizing energy. We didn't have any intention, but later we kind of checked it out how bad it is, okay? And then again, we said, what about automation? So let's change that human-driven vehicle into an automated vehicle. And you can see immediately that the situation gets much better. Okay, so it's cutting back on the on brakes in general, much more than the human. And here is a zoom when you can see it's doing a little better than the vehicle had, right? But it doesn't have any foresight. It doesn't see so far. So the energy gets a little better, but what happens if we do connectivity? So once we start to talk to multiple vehicles, and this is kind of the configuration which we did the initial experiments on the track, then you can see that this fuel consumption starts to climb down. And also, it's hard to judge, but it's actually on average, we start to reduce our speed less and less. You can look more ahead, and actually between these two, we were running exactly the same controller. So even if you didn't know whether you talk to the black vehicle or the green vehicle, it's okay. We are robust to that change. So we are robust to changes in the network structure, and it gets actually better and better. And finally, when we reach this kind of high penetration of connectivity, again, this was a toy experiment, but then we could see that it's doing much better. The energy is doing certainly better, and you could see that we are actually reducing our speed even less than, let's say, the green vehicle we are talking to. Okay, so if I want to talk about head-to-tail string stability between the green and the blue, we would be actually in this experiment head-to-tail string stable. Okay, so that measure of string stability we found was actually pretty useful for these experiments. Okay. Any questions? Yes.
Back to the first sign of CCC, the first result.
Of course, yeah.
The previous.
Even more, yeah. This is where we basically just it's kind of the same as ACC, right?
Right. Seems like the pink curve looks right okay.
Very good question. So what happened is that the pink person, I mean, she was an inexperienced driver, so she very was afraid. So she was keeping, and this kind of comes to Roberto's question about the distance. She kept really large distances. Okay. So in general, you will see always that
Maybe she did that because she was experienced.
Maybe, yeah, maybe she was better. That's true. That's true. But actually, I will show you that even she benefited between the different runs from the connectivity. Okay, so and that's actually you see it in almost all of these. Even this one, she's doing better than the blue one, right? So as Scott said, she was smart. So when we were comparing these different experiments, right? We started to norm the fuel consumption because otherwise some big numbers is hard to compare, and also different runs have different excitations, right? So for example, if you see the first configuration, which is essentially ACC, this is increasing as we go from brown to purple to orange to so on, and it's peaking actually the red vehicle, and then the automated vehicle cuts back a little bit. And as you said, this guy is actually doing pretty well. It's even cuts back based on that. Okay, so in that sense, it was a very good driver. And if you look at any of these experiments, you basically see the same trend. So there's an increase. Once you hit the CAV, then it actually starts to have less consumption, roughly speaking. But what is very interesting, if you compare the first experiment and the last one, so when we just used essentially line of sight information and we used all this connectivity, the difference in terms of the CAV is actually 19% energy reduction for this profile. Of course, I'm not trying to sell that this is always true, but it was very, very promising actually. And if you look at that last person, the good one, she still saves 7% of energy, right? So just because she's driving after the CAV, she's always doing a little better worse, but actually in the second last case, even doing worse, but it's still saving energy, okay? So in that sense, it shows that if you drive according to this configuration, then basically even people behind the CAV is going to have some benefits from that, okay? So we were very happy about it. Actually, we went to a truck company, and then they showed us their truck, and they said we have a much bigger problem than this, right? So we had to kind of deal with that. I'm not sure I'm gonna get to that in the talk, but it's not a proof, it's just a demonstration happens. But I have a theorem for today. I hope, it's, what's the time? 3:34 in the afternoon. It's probably okay. So I only have one theorem, okay? Because I found it really, really amazing, right? So one challenge with this is that if you if you want to do this evaluation, right? I mean, well, you need 8 vehicles, you need the road, it's kind of cumbersome. But even if you want to do simulations, right? This would take a lot, right? Actually, one of my students, Charles, he was running a lot of car sim and truck simulations. They are very, very time demanding, and of course depends on how you excite the system and so on. But we found something very interesting. So it turns out that I can bound the energy consumption of the CAV using something else, and a class K function is used. Okay, so it's class K functions, just monotonic functions basically. Okay, and this course is something very easy to construct. You basically use the Fourier coefficients of the head vehicle, which let's say in this situation would be the green one. Okay, and then you use the frequencies, and then you evaluate your head-to-tail transfer function and those frequencies and square it out. This takes milliseconds or microseconds to calculate, okay? And you can really use it as a nice energy measure, right? Because this stuff is still not so nice. I have this G function and so on, so pretty much you can only do it numerically. So you could imagine that you basically monitor the velocity profile of this vehicle, because you're talking to it anyway, or it's talking to you, and you can run an FFT on it, and you can calculate it in milliseconds, okay? And that can help you to tune your controller, okay? So it shows that head-to-tail transfer function is important even in terms of energy efficiency, and also this is a fast way of calculating. And it turns out that this, if you kind of think a little bit about it, this is nothing else but integrating the square of the acceleration. If you look at the literature, people often use this as energy. This is not energy, right? Even the units are wrong. So it's, but actually they are not so bad. They are not wrong about it, because if you actually use this as your performance measure, it's actually related to your true energy consumption. Okay, so we found it quite fascinating. And then of course later when we were, instead of rerunning these experiments, we just used the data and we put a truck there, and then we started to optimize it in simulations, right? So that was very nice to do that. Okay. So then we started to think a little bit about larger scale, right? So can we somehow use this to congestion mitigation? To be honest, this was our original idea, that we're gonna use CAVs to congestion mitigation, but we could only build 8 vehicles, right? I mean, 7 of them were like standard vehicles, 1 of them we actually built, right? But in simulations, you can actually start to think about it quite carefully, and then you start to construct these different chains. So for example, here we consider that every nth vehicle is a CAV, right? So then human, CAV, and then CAV. So this way you kind of simplify the configuration, and you can run, of course, simulations, but you also have some hope to do some analysis in this case, okay? So actually, if you run simulations, then you will quickly start to see that these CAV is indeed going to help, right? So if you look at humans, they are string unstable, they're just increasing these perturbations. But if you look at even like 16% penetration, well, I would say it's getting really better. I could even declare it as a head-to-tail string stable. And then if you increase more and more, then you get better and better. We also compared it, what we just use AVs. So if they are not talking to each other, and I'm not going to show those size, but actually it's a significant improvement. So for example, if you want to use CAVs, then already at 16% penetration, we can see quite large impact on the overall behavior. For AVs with the same setup, right, and the same configuration. So if they're not talking to each other, we only needed about 1/3 of the vehicles to be AVs. Okay, so that we found this well-tuned CAVs are actually very useful to do this. Okay, and I have to mention that these simulations kind of the worst case scenario, because all the human vehicles, they are basically doing the same. They have the same model, so they are amplifying the same frequency. So those transfer functions would multiply with each other, right? In reality, typically, I'm driving different than Scott, right? And so if you drive right after each other, sometimes I would amplify some of these frequencies, but maybe other frequencies I would attenuate. In this case, it's kind of the worst case scenario which we could construct, okay? And we could even analyze it. So we could calculate, now it's a good question, who is the head and who is the tail, right? So for the perspective of the CAV, this would be a head to tail configuration, but for the overall system, the black is the head and the tail CAV is the tail. But luckily we can construct these transfer functions really nicely because we are repeating the same block again, right? So that's why this transfer function is just multiplying the small transfer function n times, okay? And that little transfer function we can construct a similar way as we did for the three vehicle case, right? So essentially, we're designing this and this part of the transfer function, these are the humans in the middle, okay? And often we don't even write out their models, we just have a transfer function model for the whole block, right? That's also works out pretty nice, okay? So with this, we can actually construct these norm transfer functions, which allow us to kind of compare different penetrations because they only depend on the penetration rate. They don't depend on these different vehicle numbers anymore. And this is how it looks like. So for this situation, if I start to add the ADs, right? So essentially no connectivity. What in this case we find is we need about 50% to kind of push it head to tail stream stable. Again, this is a very, very conservative estimate. And then if you add connectivity, then already at 33% you can reach a similar behavior. Okay, so it's really useful to talk and get information from far ahead. And the key is indeed you start to break earlier. And that's exactly what the circles vehicles did. I heard that you didn't just break when you hit the jam, but you started to break earlier. Here it is happening in a smaller time scale, right? So it is not planned velocity, but it's actually how I'm responding to those vehicles. But exactly the same kind of principle and idea to try to use. Okay, so we found that this is very useful, and indeed we could improve the system behavior a lot. So one thing I have been hiding with all these transfer functions is, and this is what Scott mentioned at the beginning, that my background is in nonlinear dynamics, right? So in reality, the world is nonlinear, right? So all this linear analysis is only have some limitations. It's very nice, it's very neat, but as you know, what happens in real life is often more complicated. And one of the challenging things which happens is that so far I was kind of giving you this idea that, good behavior is stable, right? We can see this decreasing of the perturbations. But if I change my controller, if I make the system different, then I can mess it up and I get unstable. Okay, so the whole idea was that we are either stable or unstable, and then we want to be in the stable case, right? So that's what's going. But reality is more tricky. This is the same system shown exactly the same parameters, exactly the same humans. The only difference is different initial condition. In the sense that in this case, the first vehicle is reducing its velocity a little bit and then accelerates when it comes. And here the first vehicle reduces its velocity a little bit more and then it comes. And for the same control actions, I get completely different behavior. On one case, it's going to be equilibrium, everything is happy, right? On the right side, you got traffic jams, right? You can't get in a linear system something like this. A linear system in equilibrium is either stable or unstable. That's what you got in the top, right? But in a nonlinear system, this is possible, okay? So that's kind of a tricky business, and how are we going to analyze it? So first of all, you can see we needed some number of vehicles this thing to develop. Okay, so it takes some large number of vehicles sometimes to do this, right? Already we were struggling with 8 vehicles, right? But we can't just say, okay, half of University of Michigan comes to Howell Road and is going to drive for us. To be honest, this is interesting. We actually tried that. Maybe not to this level, but when this whole connectivity thing was coming up, we talked with Toyota and we tried to tell them we're going to shut down a whole highway, and we got all the safety pilot vehicles with V2X to come and drive for us. And Toyota actually was totally in it. They said this would be the best data set we could imagine. And that time, circles didn't exist. So, it was a long time ago. But then, unfortunately, some of the university officials, when their hands started to shake, and then they didn't do that at the end, okay? But certainly this is hard to do, right? And also like, so far, like when can you do these experiments? I mean, these were really experiments rather than empirical data. It's getting really tricky. Okay, so how are we going to solve this problem that we don't have this many vehicles? Well, we can have infinitely many. Okay, so we started with 3, but we put them on a circle, right? So this is back in 2002 when I was actually finishing my master thesis back in Hungary, and you can see a couple of weird stuff here. Okay, so number 1 is my name is in the wrong order. Okay, that's the right order, right? So Hungary, we use the family name first and then the given name. So when I go to Hungary, that's my name. Okay, when I come out, I'm Gabor. Okay, Chinese people know what I'm talking about. Okay? And then the other thing is that it's even worse. Like, so this is the name of my advisor. So his name in Hungary is Stepan Gabor, but they are messing up the end, right? So because there are all these inflections in the language, and it's a very, very difficult in the grammar. Okay. So already this was, of course, people have been doing it, and there are some famous experiments which are coming too. So this may be a way to do this, right? So because in this case, if a wave starts to develop on the ring, it can actually amplify it until it reaches that final stop and go motion. Okay, or if we are doing well, then it actually can calm down, and then we can get the equilibrium back. Okay, and then so this is. Probably many people in this room know this what we do. So basically put these vehicles on the ring, we make periodic boundary conditions, and then we come up with some car following model. Okay, and this could be, well, I think first principle based is, I'm not sure that's the right way to say it, it's a hunch based often, right? But it could be data based, right? So you could learn this from data as well. But we know it's nonlinear. And there's another important thing happening here, which I so far kept hidden, and that's the reaction time delay of drivers. Okay, so we actually measured it. So I can tell you in my group, the reaction time delay of people, this is a distribution typically, so I'm only telling you the mean value, right? It's between 0.8 and about 1.1 second, roughly. Sergey is 0.8, and it already includes the vehicle's reaction time, right? So it's basically from the stimuli, which is listed here, right, until we see acceleration or deceleration, okay? And then some of my students who were non-attentive drivers, it could go really bad. It can second, right? It's really, really very dangerous. So I never let them drive like that. Anyway,
How about the ones that are looking at their iPhones?
Yeah, actually, okay, this is the part I don't want to talk about. Okay, so the important thing is that this is actually nonlinear, right? So a couple of nonlinearities here. So for example, we have these saturations, right? You won't be able to accelerate, too high and brake so high. So your braking limit is typically less than 1G. In a normal car, acceleration is 0.3 G or something like that. Okay, electric cars are getting much better in that. And of course, we also have nonlinearities in the human behavior. So this is that classical optimal velocity model, which I already mentioned. And you can see, for example, this range policy or optimal velocity function, you can see that it's indeed nonlinear. Okay, so clearly these nonlinearities are there, and these are behind this phenomenon. Okay. And what we found is when we analyzed this system that we could identify these different motions. So we could find the equilibrium, okay? So in the velocity, this means constant velocity, constant headway, and this in a state space diagram, it would be just a point, okay? And you can see these kind of brake and accelerate back type of solutions which come out of the equations, and they are actually unstable. And then we also see the stable limit cycle, which is a stop and go oscillation, okay? So the way we actually observe these unstable oscillations is exactly what I showed with the simulation at the beginning. If the perturbation is less than the amplitude, so this is now it's an open chase simulation, right? Guys stepping on the brake, accelerating back, it's weak enough, then it decays, okay? So basically, you perturb the system, but you couldn't go over the threshold, and then you kind of settle back to the equilibrium, okay? If you press that brake pedal harder and come back, then you can actually generate these large perturbation oscillations. Okay, so this is the skeleton which is behind this bistable behavior in the system. Okay, so this is
all of that is with constant uniform delay.
Yes, so in this case, all the delays are the same, all the people are uniform, and indeed you can make them more heterogeneous and so on, but you will see the same behavior. Also, it's not car flowing model dependent. We could get the same thing for the IDM and for the OVM. So that's well, I'm sure there are many more car flowing models, but at least for those you can get it easily. Okay. And so this is when you kind of settle down and go back to the equilibrium. This is a very old simulation. And then in case of a little harsher perturbation, you will see it starts very similar. Actually, the beginning is almost the same. You can see those braking vehicles. This shaking is just the video frame. Okay, so that's not happening there. And then you can see that we break down and we actually start to see these oscillations. Okay, and once you are in this stop and go motion, of course, it's very difficult to get the system back, right? It's typically start to play with the demand and so on, and eventually you can get rid of it. Okay. And then I will skip this. What happens if we add the CAVs? Okay, so suddenly things starts to get more complicated. So now it's on the ring, okay? I still have these human driver behaviors, which I'm using the OVM here. And I have the CAVs, okay, which are now I'm designing, okay? So I'm selecting those gains, I'm choosing this range policy and things like that. And they are very similar, right? Essentially, the only difference is that the CAVs in this situation, they can actually look ahead, in this case, N vehicles, right? And get information, also respond to that vehicle. So it's an N vehicle look ahead model, right? These things has been around in the literature for quite a while, okay? So the other interesting thing is I also put the delay here. And you may say like, well, wait a minute, this is an automated vehicle. This is supposed to respond, much better than a human. So last year I went to the ABEC conference that was in Milan, Italy. Weather was like this, okay? So just because you go to a possibly warm place, you may not get the weather, or maybe just me, anywhere I go, carrying the rain with me, I don't know. So the European Commission made some measurements on the Mercedes S-Class. Okay, that's a quite expensive vehicle, which now has this level 3 automation. Okay, and the only thing they did, they hired that car, they drove it on the highway or made the car drive itself, right? And then they were measuring the time delay. Mercedes S-Class has 1.2 second delay. That's worse than anyone in my group. So we were waiting for all these AVs that they are so fast and they certainly can do many things better, right? They are more consistent, they don't fall asleep and so on. Their delay is higher than the human delay. Because what do they do is, they have 10 cameras. They bring in all that camera picture. They run the neural networks on it. They figure out what's going on. Then they fuse that information. Then they probably have LiDARs. They also do the same thing with the LiDAR information. They all come in together. They do some computation. And finally, they step on that brake. From the time the vehicle sees the stimuli until it presses the brake, it's 1.2 seconds. It's worse than a human. Okay.
In all kind of scenario, or is it in certain scenario?
So that's a very good question. At that time when they were testing, the Mercedes S-Class was allowed to drive on the German Autobahn below 60 kilometers per hour. I'm not joking, below 60 kilometers per hour. So exactly, yeah. So you could only use it. Now they are trying to crank it up a little bit more, right? But this is how the auto industry works. They kind of try to improve it. So certainly not in all situations, right? I'm pretty sure that if you drive on an open road and nothing happens, this would be different. You have one vehicle in front of you, everything gets simpler. But in particular, in those situations when you would really need it, you actually have pretty large delay in the system, right? So you can't just neglect that.
And sorry, does that delay depend on the initial condition, or is it just constant for every region?
So I would say it could depend on the state in general.
Otherwise, you would collide, right?
Yes, you're absolutely right. So certainly, like when two vehicles are 5 meters apart and so on, then you're probably different, right? So this is obviously they got a distribution, and this was the mean of the distribution, right? In those situations, it's probably less. Yet we can't omit that in the system, right? So we can design these controllers much better than we do with humans who we can't design, but we certainly have to deal with this. And then, of course, we also have nonlinearities. To be honest, even the range policy of the vehicle is nonlinear. We try to make it as linear as possible here in the middle, but somewhere we have to saturate, right? So this will be still there. And of course, they also have the saturations in the acceleration. Okay. So we were like, can we do this in measurements? Okay, so this is our circle. It's U of M. So if you ever been to M City, then you have seen this. Again, the shaking is just the video. So we tried to do this experiment, right? And of course, at the same time, a very famous experiment was born down in Arizona, right? When they had much more vehicles, and it was very successful. This was our very unsuccessful attempt, I have to say, okay? So let me tell you why did we fail. So if you look at, for example, the data in that famous experiment, I think your maximum speed was 12 meters per second. And looking at your circle, which is about 40-meter radius, your lateral acceleration was 0.35 meter per second square, which is, as we discussed, a reasonable acceleration for humans, right? If you start to increase that speed, right, or make the circle more tight, this goes up really bad. The reason we failed in this experiment was drivers were constantly focusing on how to drive, how to steer the vehicle, okay? So as a matter of fact, one other question, so, but of course, this is a trivial question here. So why are we driving counterclockwise?
NASCAR, Northern Hemisphere.
So that's a good question. If you look at the Sugiyama experiment, they're driving clockwise, right? You guys also drive counterclockwise. Why? The driving side. Yeah. So the British and the Japanese experiments, they always drive clockwise. The American and European experiments, we have to drive counterclockwise because it's easier for the driver to see, basically. Yeah. But again, we failed with this, right? So you're like, this is not gonna work. So can we do something? And again, we didn't have too many vehicles. We also didn't have a very large space where we could spread them. So then we came up with an interesting idea. Okay, and we call it the virtual ring. So what we did was we put a chain of vehicles. Okay, so this was the CAV. Now you can see this is at the front. Okay, but we made this guy believe that this guy is in front of him. We projected this data here, and thereby we created a circle.
Oh, fun.
Okay, so basically the blue vehicle drives believing it's on a circle, while in reality it was driving in a straight. It's really funny, okay? When I was driving this car. When I step on the brake in this one, okay, something interesting happens. So I start to slow down. The vehicle behind me, which is the CAV, it actually also starts to slow down. So it basically runs ahead and stops somewhere on the road, right? Because it's driving behind me, right? So it was kind of funny to deal with it, but it was something giving us an unprecedented opportunity to drive with really high speed. So here is one of the experiments we did. As you can see, we easily reached 25 meters per second, okay? The ring length in our case, which is basically the space between the vehicles, that's L plus the vehicle length, that was 90 meters. If you try to drive it in a 90-meter length circle with this speed, the lateral acceleration would be 4.5 G, okay? Sergei can bear it, but even him, for a very short time, that's race car driver, you won't be able to do that, right? But in this case, our lateral acceleration was 0. We were driving straight on the road, okay? So this allowed us to, for this very simple thing, to even check this bistable and nonlinear behaviors. And you can see what happens here. The red vehicle steps on the brake. The vehicle behind it is responding to that, right? The vehicle behind it is responding to that, and of course, so on. And you can see that in this case, when I step on the brake, there is some perturbation, but it nicely goes back to the equilibrium. This perturbation was not strong enough to trigger the jam. Once I step on the brake a little harder, okay, again, there is a response from the vehicle. And you can see we go to this, but it's not a stop and go, we only have 3 vehicles, right? But we go to the sustained limit cycle oscillations, okay? So we were very happy about it, that we were able to show that indeed, this thing is there, and of course, we needed the nonlinearity for that. And then we also said, well, can we do better than this, right? So this is what essentially an AV plus 2 humans do. If we really start to utilize connectivity, so now the blue vehicle looking 2 vehicles ahead, right, on the ring, this is 2 vehicles ahead, and taking it, and we couldn't even push it into an oscillation. It became globally stable. So it doesn't matter how hard I'm stepping on the brake, the system always going back to its equilibrium. Okay. So it was really nice to do it, and it was a little bit harder to explain to the police when they came what we are doing, but I kept some of the details from them. Okay, it was kind of fun.
Do you
Yes.
get the results theoretically to be proven to be actually just oscillation die away, or is it simulation based?
No, this is the experiment.
No, I mean, is it possible to do it in theory to show that the
Yes, so indeed, it's a good point. Now I understand. Yes, so you can actually show that with certain parameter selections, right? And indeed, the main point is exactly that we add this additional link, then you can actually make the system globally stable, right? So again, it's toy configuration, but we were pretty happy about it. We were to do that.
I have a question, where were you driving and how come you were you alone in the road or because
Yes,
you got
yes.
another vehicle?
Yeah, so this was, so Scott asked that question earlier. So yes, it was a lone road, basically. It's a public road, but no traffic. It's farmland. So your only danger is that basically you're driving these sedans in a farmland. And then all the farmers like, what the heck is going on? So eventually they call the cops.
And he's an invader.
And you need to explain to them what you're doing, and you have to be smart how you do that, right? So that's the idea. But yeah.
So what happens when you kind of shrink this virtual circle for 3 vehicles? Have you tried that or?
So if you shrink the circle, then basically you make traffic more dense, so it becomes more unstable essentially, right? And of course, you can shrink it so much that eventually they stop. So we actually played with the ring lengths because that was easy, right? Here it's just a code, and we just say, okay, ring length is 9 meters. And so when they were really close to each other, they just stop, right? And they don't do anything. Actually, it's interesting because again, that car runs ahead and stops somewhere because it's stopping behind you, right? You always have to think a little careful about it. But yeah, so then that's what happens. So we like, and it was an important parameter, of course. So that way we kind of play with the traffic density, right? Again, these are kind of we have to be careful how we.
But it doesn't get unsafe at that point.
So this is actually very interesting. You see, in the other experiments, which I was showing with the 8 vehicles, we really needed Sergey in the sense that, if something went wrong, Sergey would stop and brake. In this case, this guy is not gonna hit no one, right? So it was much more safe to run this experiment, right? Because no one was in front of the CAV, right? So that in physical reality, right? So in that sense, it was good.
I have a few too many, so I won't go into all of it. First, what are your thoughts if we change the vehicle type to heavy duty vehicles, and what would that look like? Would that have a more positive or negative impact?
Okay, so let me answer the question a little longer at the end. So
Yeah, go.
I will. So first of all, Scott already spoiled the video, so now I'm gonna show the video because he was waiting for that. Okay, so that's our motivation, and then I answer your question. Okay, so let's do this way. So that's the famous one, right? So now it's in its 7th or 8th installment, something like that. This is actually Mission Impossible 3, right? This was 2006. So
I thought it was. I think it's the first.
no, it's actually the
It's the third. I'm wrong. Okay.
Third one. Yeah. And you can see that, first of all, you can live for 20 years of playing a secret agent and also doing traffic. Right, so that's the other thing, but I show the video and then I answer your question. Okay, so this is kind of the true motivation.
Department of Transportation.
I've been there over 10 years now.
What do you do at the DOT?
I study traffic patterns. You hit the brakes for a second, just tap them on the freeway. You can literally track the ripple effect of that action across a 200-mile stretch of road because traffic has a memory. It's amazing. It's like a living organism. Freshen that up for you. Was it vodka martini?
Yeah.
Ladies, did you?
I'd marry him.
I would too.
Okay, so maybe one last thing before I answer your question. So if you're interested in more, there's an upcoming book with Tamás Molnár, which is kind of containing more information than this, but also these results are there. It's not yet out. If you're interested in it, I'm happy to send you a copy. Should be out sometime this year. Okay, so that's the thing. Okay, so thank you very much. And then
But we have a few questions in chat, it looks like.
yeah, so let me answer your question first, okay?
Okay.
That was very interesting, okay? So this is our toy, okay? Just to kind of put you into context. So this is a Dodge Charger. Thank you. Nice to see you. So this is the Dodge Charger. It has a 400 horsepower engine. It's a classic American muscle car, okay? This is a Navistar truck. Okay, it has a 400 horsepower engine, okay? The difference is that this is less than 2 tons. This bobtail, as we call it, is already 9 tons, okay? And then it's supposed to tow another 21 tons, right? So it's basically a 30-ton things with the same powertrain as the car behind it. So to answer your question, it does influence a lot because there are much bigger lags and delays in the system, right? Once you try to, for example, accelerate with this guy, I mean, this has a automatic gear shift, you see speed dropping when you change the gear, right? So you go up and so on, right? In the electric, it's a little better, but still, you know, mass is important. And then we also check the delay in the control loop. So while the automated vehicle, if we don't calculate all those sensor delays and so on. So just basically the mechanical delay is about half a second, right? Or maybe even less. I think electric's like 0.3 seconds, roughly like that. That's again without any computation, any sensing. That's just a kind of actuation delay. This already 0.7 seconds. So whenever we try to do, for example, safety tests, so we run the same experiment with this truck. When we try to brake in front of it, with cars it worked totally fine. In the truck, we actually crashed into the other car. The only reason I didn't die because I drove the car in the other lane, basically. So we did the experience that I'm driving in one lane, and then of course connectivity could help us to calculate the distance. But basically, this guy came through me, right? If I was driving in the same lane, I wouldn't give this talk. So indeed, there is a lot of difference there, and it comes to the fact that we may want to kind of assign a certain motion, but control is much harder. So that's basically the answer on that. And then there was some in the chat.
Oh, no, I think it was just John.
Okay, then
Oh, that's just John?
Paper.
Okay.
Okay.
So the energy data, the energy results you showed earlier, did you also collect the real energy consumption from the cars?
Yes, so for the cars, no, because these were rental cars, right? So we could only calculate this kinetic energy based energy, right? So that was the only thing we could do. And we roughly have an idea about their rolling resistance and all those things, so we could calculate it. But we don't have fuel consumption on those. For the truck, we actually built a fuel consumption measuring system, right? The issue with those is that we could see the same trend. So I can say with high confidence, we saw the same thing, right? But the quantitative things are a little tricky because those fuel measurements are very unreliable. I mean, you're supposed to measure instantaneous fuel consumption. Of course, if you measure from beginning to end, that's fine, right? But when we were actually running that, what we found is on real roads, when running this in not heavy traffic, so it was light traffic, in terms of kinetic energy, we could save about 5%. Okay, and that included an optimization for the grade, but it also included responding to other vehicles. So let me see, maybe I have a video about this one. Yeah. So in this case, we were switching between, sorry, so slow. Yeah, how to make it smooth. Okay, put it up. Then this way, hopefully. Is it this slow? Oh, it's coming, yeah. So and then yeah, so this is one of the tests we were running. We're following another vehicle. And here we are running this energy optimization based on the elevation, okay? Then the other vehicles tap on the brake. We have to activate the connected cruise control for a while, but then eventually we can go back to the energy. So in this case, we measured, and in track, of course, we're doing 15%, 20%, right? Because that's how we designed the experiment. On real roads, it was about 5%. So that's how far we can go with that. But again, fuel measurements were in general quite unreliable. It was hard to measure that. So in all the publications, we always use this energy consumption. And one advantage is that even if you have another powertrain like electric, then you can compare it, right? But in reality, how you manage your powertrain and so on, that's a whole other topic then. Yeah. Yeah.
I would like to know how you model the transfer functions that you analyze the head to tail stability.
Yeah, sure. So if I may. So in case of for a human, right, it becomes relatively simple. So the human's transfer function is beta times s plus alpha. It's e to the s tau times s squared plus alpha plus beta times s plus alpha alpha. So this comes from that human model where alpha is the gain for the distance, the beta is the gain for the velocity difference, tau is the time delay here. This is a square, just I'm writing, and the kappa is the range velocity gradient. So these are this simple or this complicated basically. And when you have the automated vehicle, it gets a little more complicated, so especially the denominator, and then you're supposed to multiply them and do some manipulations with them. But it's relatively easy to calculate them. So you linearize the system, you do a Laplace transform, and it's a very standard thing. And this is what the question was I got when I interviewed at Michigan by Jeff, actually. He was asking me, how is the transfer function? Because I was telling all about the circles and nominal dynamics, and he's like, give me a transfer function that gives me a little more understanding. Yeah. And you can see that it's always 1 at 0, right? So if you see any article and this is not true, then you know that you should reject that paper, right? Because that would shift the equilibrium. So it always have to start at 0. And then what you want to have is that, you know, for a back human again, this would go above 1, right? For some frequency regime. So something like this you're gonna get. But for a good behavior, you want to keep it down below there. Okay. So that's the idea. Again, the head to tails are more complex, but they are kind of compiled from these little blocks. So this kind of gives us a very efficient computation to do these things.
And for the theorem you presented, you said that you could bound the energy, and by computing the FFT, you can also tune the controller. So
exactly, and that's why we did that.
So you're tuning in real time, or it's something you do offline?
So potentially you can do it real time. We never did that, right? So what we did is once we had the data, we were running the FFT on the data, and based on that, we tuned the controller. The only thing we kind of did is that we looked at different data sets. For example, those kind of braking and acceleration parts. We also have another data set. We do kind of like step functions, and we have like highway driving. So we cross-check that if we tune the gains on one of the data sets, and this is a fancy word, how generalizable it is to other cases. And we found it is pretty good actually. So interestingly, there is an area in the parameter space where you are robustly head to tail string stable. So even against human uncertainties, you're doing well, and actually even your energy consumption is pretty good. And that kind of helped us to identify those areas.
All right, thank you, Gabor, for honestly, this was amazing in particular because what you presented is just so deeply relevant to many people in this audience. So thank you so much. Very informative and inspiring. Thanks.